Recording in progress.
The Indian Association of Structural Engineers, also known as IIA Struct E, was conceptualized and constituted in the year 2002 by a group of senior professional structural engineers from all over the country. IIA Struct E is registered under the Societies Registration Act 21 of 1860. IIA Struct E is a national apex body of structural engineers in India with a mission to promote structural engineering profession and cater to the professional needs of the structural fraternity. In the short span of 2 decades, association has attained an eminent position in the professional field. Its membership is valued very highly in the profession. Since inception, IIA Struct E has been led by eminent structural engineers like late Shri Mahendra Raj, late Shri Kumar Ghosh, Shri Subhash Chand Mehrotra, Professor Mahesh Tandon, Shri Alok Bhaumik, Shri Manoj Mittal and Professor R. Pradeep Kumar as its president. IIA Struct E is a permanent member of Engineering Council of India and interacts with the government on professional and policy matters related to civil and structural engineers. To expand its reach, IIA Struct E has collaboration with various international professional like-minded associations and institutions. IIA Struct E's prime objective is supporting and protecting the profession of structural engineering by upholding professional standards and acting as a mouthpiece for structural engineers in India. IIA Struct E endeavor to ensure that its members develop the necessary skill in structural engineering and work to the highest standards by maintaining a commitment to professional ethics and standards. IIA Struct E is actively engaged in organizing several continuing professional development (CPD) courses for structural engineers to help them update their knowledge and advance their career paths. It also conducts refresher courses for young and practicing engineers and student-oriented programs, seminars, workshops, conferences, technical lectures and discussions related to the latest technological advancements, and case studies are also organized regularly for members to enable them to continuously update their knowledge and skill set by interacting with the best minds from the industry. IIA Struct E's activities are widely appreciated and known for quality technical contents. IIA Struct E is also actively engaged in publishing its quarterly journal Structural Engineering Digest (SED), code commentaries, professional guidelines, and a monthly newsletter. IIA Struct E's publications are becoming popular with time. IIA Struct E has representation in various technical committees of BIS and IRC as well. Its members are actively contributing to National Code of Formulations. In the year 2020, IIA Struct E started National Awards competition to stimulate interest in the structural engineering field and to promote innovative thinking and creativity. The awards are presented to the winners in recognition of their outstanding contribution to structural engineering in the categories which include Outstanding Structure, Outstanding Structural Engineer, Outstanding Woman Structural Engineer, Promising Young Structural Engineer, and Best Master's Thesis in Structural Engineering. IIA Struct E is currently operating from 4 regional centers, namely Eastern, Western, Northern, and Southern, having its headquarters in Delhi to inculcate the professional culture and provide handholding to the budding engineers. IIA Struct E has its student chapters in several leading engineering institutions as well. Membership of IIA Struct E is open to all civil and structural engineers engaged in structural engineering profession. Members are elected based on their qualifications and experience in different grades as per eligibility requirements prescribed in the bylaws. Each application is carefully scrutinized before electing the members. More information about IIA Struct E is available on its website www.iastruct.co.in.
Good evening. I think Abhijit, you
Yeah,
can
I
start
can.
the
Yeah.
program. Yeah.
Good evening, everybody. I hope you can all hear me well. Today, we are going to see something different than normally what is seen in India. It's expansion in vertical direction of the buildings. So we have Dr. Bujur Murwa, who is a 25 years of experience in tall buildings. He's a consultant with RWDI, senior consultant, and his expertise are in wind response of tall buildings, performance-based design, then structure optimization, dynamic sensitive structures, and design of supplementary damping systems with RWDI's motionary wing. He is a member of ASCE, American Society of Civil Engineers. He's a member of American Concrete Institute, ACI, and is a committee member of ASCE, ACI committee, ACI 375. We look forward to hearing him. Dr. Bujur, welcome for this session, and floor is all yours. Please enlighten us with the discussion and the findings that you have for this vertical expansion. Dr. Bujur,
I can hear
us?
you.
Yeah, okay. So you can start, Doctor.
Dr. Buzar, you can start your presentation. Can you share your PPT, please?
Good afternoon. I can hear you.
Oh, you can't.
Oh,
Okay.
Yeah, now I can hear you.
Now you
okay.
can. Okay, great.
Yeah.
So we just great. So we introduce yourself. So you can probably start the presentation, and then let's get on with the topic.
Okay. Let me share my screen first. Can you see my screen?
Yes,
Yeah.
we can
Yeah.
see your screen.
Okay.
You can make it presentation mode, please.
Yeah, I can start with the slide show now.
Yeah.
That should be full in there.
Yes.
Okay. Is everybody ready now, Abhijit?
Yes, please.
Yeah. Dr. Buzar, I think we are seeing two slides. If you can just change the display setting.
Oh. Okay. Is it okay? Can you see it now? It's still in one or in two?
No, we still we are seeing two.
Oh, the upcoming slide as well. That's what.
Yes.
Yeah, yeah.
Yes.
Okay. Well, let me change that in which screen.
I think on the top, if you see the display setting.
Okay.
Yeah. I think swap. You can swap or.
Is it okay now?
Yeah, it is fine.
Much better. Yeah, perfect.
Okay. Well, good afternoon, everyone. My name is Buyar Morava. I am a senior consultant with RWDI in Canada. And in today's presentation, I'll be talking about a unique project that has been completed a few years ago here in Canada with a focus on a vertical expansion that it's been done for the first time with where an existing office building with 18 stories was expanded vertically up to 57 by adding on top of an existing structure another 37 floor residential. This building, if it happens that you are visiting Toronto in Canada and are ending up on the end side of the downtown area, you won't miss 480 University Avenue building, which is shown in this line. It's at the northwest corner of University Avenue and Dundas Street in Toronto. From the first look at the building, if you are as a visitor and don't know exactly what's going on behind this building, it may look like another modern condominium building, but actually right behind the lower portion of the structure, it's maintained and preserved an existing building structure of an 18-story building that was completed in 1968. It's a reinforced. You see that on the currently on the right-hand side on the slide. That building was completed in 1968, a reinforced concrete structure, and what turned out of that structure, preserving it and going with a unique, innovating structural solution to expand it vertically in a modern, spectacular mixed-use development that you see on the left-hand side, the completed one. It's completed in 2019 with total of 57 floors and a total height of 280 meters. 480 University Avenue, it's redefined what's possible in a vertical expansion of building. Before going to all the technical details of how this was achieved, I want to also mention that this building is the winner of CDBH 2021 Award of Structural Engineering Excellence in the Renovation Award category. Well, the question is, what makes this building so unique? And what I've summarized in there, 3 key points. It's the first ever designed and constructed high-rise building where an innovative vertical expansion concept was conceptualized and implemented. Secondly, it's the first ever high-rise building which is equipped also with a damping system, a spread tuned bidirectional tune sloshing damper, the performance of which was verified and validated through long-term structural monitoring. In addition, the design of this, the architectural structural design of this building considered also was based on sustainable design principles. What I mean by that, there were 3 key elements that were part of the sustainable design considerations for this building. The existing structure was preserved. The lateral system of the structure, and also the foundation, being a caisson foundation, was able to be expanded further with 4 more stories, parking levels, reusing completely the existing foundation system as well as the lateral system. So instead of going through the option of tearing down, demolishing the building and building completely a new reinforced concrete building, some key elements of the existing structures were preserved, and with a very unique and quite daring structural solution was made possible to achieve this kind of very intense vertical expansion of this building. So what was the fundamental structural concept applied in here? So what you see on the left-hand side here, it shows again the existing building. When as a first step, a very detailed structural assessment of the building was done on site, and all the design information that was used originally for the design of the building. The whole idea, what was found on that, is that there is a perimeter concrete framing on the structure that was connected with a central core on the existing building, very conveniently laid out in a way that an outer tubular exoskeleton structure could be implemented, expanded up to the top of the building, and creating a powerful transfer structure as a composite steel and reinforced concrete to create to give the possibility of redistributing the addition load, gravity load, and lateral load due to the wind of the 37 additional residential floors on top of the transfer structure. The idea was to manage both the gravity and the lateral wind loading through this transfer structure out to the perimeter tubular exoskeleton structure. In all this evaluation, there were important some key factors that gave the confidence to the design team that is possible. And here what I'm listing the three key factors that were gave the green light to proceed with this concept. First is the fact that the existing building was sufficiently set back from the property line, which allowed to add the exoskeleton steel structure. Secondly, there were two centrally located mechanical risers, which allowed the addition of two 800 millimeter thick shear walls. And thirdly, the building was supported on caissons, which allowed the addition of 4 levels of parking underneath the existing 2 initial ones that were part of the original design. So here is how the original ground floor looks like. So what you see around here on yellow is all the area available around the existing building to introduce the additional structure to make possible the transfer of the gravity and load, as well as the lateral load of the 37 floors added on top of the existing one. If you see carefully around, on the west side, there is a 1.7 meter space from the structure to the property line, and so very limited on the south side, right along the Dundas Street. On the east side or north, there were more space available, which allowed to add some front store retail areas and integrating that in the new architectural design of the entire building in terms of the massing. Then when it comes to the key elements that were part of the new lateral scheme were the available mechanical risers on the existing building, servicing the 18 floors. The north mechanical risers, as shown on the screen here, and the south mechanical risers. Those risers had enough footprint area which would allow the building construction of two shear walls that were expanded down to the bedrock, to the engineering bedrock, where the caissons were supported, and developing this up, expanding those up above the existing building and integrating into the transfer floor. When it comes to the load transfer concept, what I've summarized in here, you can see in red, right at level 20, is where the concrete and steel powerful transfer structure was located, and it's a grid line of beams, deep beams running in the north-south and east-west direction. What you see in here, that's the section north-south section of the building. And all the gravity load through the transfer plate and transfer beams were redirected into the perimeter of the structure, as you see with the dotted red lines there, through the exoskeleton structure. And in the middle, you see the powerful shear walls coming down from the bedrock, the new foundation, up and connecting with the transfer plate. At the bottom, through a top-down construction, 4 additional parking levels were added by removing all the soil surrounding the caisson foundations, and with the top-down construction approach, the new slabs poured as slab on grade slabs across the entire caisson, existing caisson system. That allowed also the bracing of the old caissons that were used fully and reinforced to brace laterally the existing caissons from level parking 1, 2, and stretch on the others below. Now, with regards to the creation of the exoskeleton structure around the building, what you see now in blue is all the perimeter. They were introduced 24 perimeter columns, sister columns, that were attached laterally only through a slip joint with the existing reinforced concrete columns. That allowed to transfer the gravity load with the total gravity load and the additional axial load coming from the wind action was transferred fully with no sharing with the existing gravity columns, but laterally the lateral system of the existing building was able to be integrated into the new and connected with the new exoskeleton tube structure. The new shear walls, what you see in here, are shown right at the existing risers, mechanical risers, up to the transfer level. So this is right. This slide, what I'm showing here, is just the exoskeleton structure, and the internal existing reinforced concrete is removed to give an idea as to what kind of system was implemented externally through the exoskeleton to make it possible to transfer the entire gravity load of the 37 new stories to the exoskeleton structure, as well as the introducing the very critical slip connections shown, slip joints shown in blue in here, that would allow to connect laterally to allow lateral transfer loads from the exoskeleton into the existing reinforced concrete system. To give an idea how this system would look like into the entire building, I'm sharing here an architecture rendering of the exoskeleton's erection. So in addition to the sister columns, the vertical ones, the tubes that run from the foundation up to the top of the existing building, then the bracing to connect to that also to increase the torsional stiffness of the new tubular system, which is integrated now into the existing reinforced concrete columns and the existing, through that connection horizontally, existing core of the office building. As I mentioned earlier, the most critical connection here that needed the particular attention was the slip joint between the exoskeleton columns and the existing reinforced concrete columns. What you see on the right there is the detail of the slip joint, which would allow the settlement and the shortening of the steel columns as the gravity load was growing up gradually through the transfer system, the transfer slab, and up as all the typical residential floors were added into the building, into a conventional construction of a reinforced concrete building, residential building. Now, the one important thing to mention here, throughout all this process, as the transfer, once the transfer plate was completed and the new construction above level 20 started, the building was surveyed very thoroughly through the entire perimeter to confirm and make sure that the settlement of the columns was done properly, evenly. And all those data were showing consistently a variation, a differential settlement within 2 to 3 millimeters through the entire exoskeleton structure. And that gradual shortening as the exoskeleton was taking the load, they could monitor as well the movement on the exoskeleton, the contraction of the columns on the exoskeleton structures through the slip joint. That allowed that kind of low deformation to be accommodated without any additional stress to the structure. Now, the addition of the exoskeleton structure in the perimeter allowed also a very elegant facade, new facade incorporated through the attachment of that completely into the exoskeleton system. What this rendering here is showing was at the early stages of the design to visually confirm how the things will be integrated with the interior design elements, and also detailing how the facade, the new facade, would be mounted into the exoskeleton system. In integration of the existing building and structure was for sure, right, the key consideration from day one as the design concept moved further into schematic and then into the construction document with a clear plan that at the start of building the additional exoskeleton structure, three activities would continue simultaneously. And that's what this slide is showing here, is summarizing. At the lower sections where the columns, exoskeleton columns were coming and then being constructed at the same time, a very important consideration of the implementation of the solution was that the building was maintained, were to be maintained operational throughout the construction process. So what you're seeing here as the construction continues on the lower portion with the new exoskeleton structure, 3 floors above, simultaneously was happening the removal of the old precast concrete panels that created the facade. In the meantime, inside the building, the business was continuing as usual. Certainly was also a lot of coordination. If you see here, it was some temporary drywalling was added into the outer facade of the previous of the old building to make sure that the noise was limited to the maximum level possible, and also for the safety reasons, because throughout this exoskeleton construction, a lot of construction activity around the existing buildings were taking place. To give you an idea as to how this process, and those were all checked, and to the every step, how this process would have been developed and executed. This is an architecture rendering again of the existing precast facade extraction. A very specific, unique device were designed, air constructed, to make this process time efficient and also safe removal of these panels, because all around the building during the time that exoskeleton and later on and the old facade removal, there were a lot of activities on the ground as well. So on the ground, inside the building, business as usual, and in parallel, the construction process was progressing, all right, with clearly defined and coordinated steps. So this is what this is schematically showing, how each of the panels modules were to be removed, creating space for installation of the exoskeleton system columns, and at the same time progressing up by removing and clearing the floor around the building for the new columns and bracing system to come in. So here is that device that was designed and constructed for this very specific purpose. That was operated through the tower crane of the building was holding, and at the same time, the crew on each floor was operating, coordinating with the removal of all the small panels and safely brought down on the ground to allow for the growing of the exoskeleton structure around the perimeter of the building. So when it comes to the one of the key elements, and obviously at the same importance structurally as the tubular system around, was the transfer floor at level 20. So the way this system was conceptualized was to run two powerful 3-meter deep longitudinal beams. That's what you are seeing here. The big ones are running north-south, as well as 6 other cross beams running in the either side of this deep longitudinal ones running east-west. 12 of those. And in addition to this, all the system was tied around with a perimeter transfer beam with a depth of almost 1.5 meters all around. So this allowed to achieve the objective of transferring all the gravity load of the 37 stories built above this powerful transfer floor, which you can call it as well. I also label it as a mid-air foundation. Actually, that's what it is. It's another big foundation, almost mid-height, 1/3 of the building, that allows the transfer of the loads. The ratio of the gravity loads spread between the shear walls, the two 800 millimeter, and the exoskeleton was 55 to 45%. So 55% of gravity loads was distributed and taken care by the two centrally located shear walls, and the 45% equally spread on the exoskeleton columns. This concept is also known for a smaller application as a sister column system, where you are adding it right next to the existing column, another one that helps in increasing, transferring the lateral load, but also taking care of the gravity loads that come from the above. Now, again, to get a better understanding of how the things were to be coordinated, everything was followed up with a 3D rendering to get a clear picture where things are going and how the end product will look like at the completion construction-wise. So what you're seeing here, you have the grid of the beams, with the deep ones running north-south from left to right on the slide, and then the secondary 2.2 meter deep that's running east-west and fully connected with the deep transfer beams. And what you see, those two floors there underneath the transfer slab, those were also used as mechanical space, as well as an amenity floor was created. There is a pool also for the residential units on the west side of the building, of the floor plate, right under the transfer floor. I'm pretty sure you also would be interested to see how in the real life this system, this big transfer system look like. What you're seeing here is right at the completion of the south shear wall, just protruding above the level 19, and it's right at the finishing of the expanded wings of this powerful wall. A wall that was going to support the big longitudinal beams running from right to left on the slide. And here is during construction of the transfer beams. From the left to right are running the longitudinal 3 meter deep beams, and from right to left are the cross transversal beams at 2.2 meter. It's a lot of structure in there, and the pouring of concrete was in multiple layers with proper care to keep the continuity till we are hitting the top of the transfer floor. From there on, the construction continues like a typical reinforced concrete condominium building. And in a different view here, what you are seeing is now the two longitudinal beams near completion of the positioning of the rebarring, and getting ready for the concrete pouring on these two powerful and very critical elements of the transfer system. As I mentioned previously, above the transfer plate, the system switched into the traditional conventional layout of a central core system with with shear walls that demising shear walls that also define the boundaries between the units. And this configuration and layout continued up from level 21st up to the 57 above the transfer plate. And again, with the same pattern, an architecture rendering you see in here just creates the images of how the conventional floor plate will be developed and constructed right above the transfer structure. In this slide, I'm showing the construction progress of the typical residential floors, and in parallel, the addition of the new facade on the building. And this, right after the completion of the transfer floor, obviously, the pace of the construction changed drastically and allowed the construction team to catch up with the delays and the time consuming, which was definitely required to build all that very complex structure, exoskeleton structure around the building and the transfer floor. The addition of the 4 underground parking levels as part of the new foundation system was perhaps much more challenging actually than what additional work was done on the exoskeleton. Keep in mind that all the caissons that were put in place back 50 years ago was shown there on the left-hand side. All the soil had to be removed in a well-planned approach to allow for introduction of the new foundation. That what you're seeing here is right at the bottom on top of the bedrock, the placing of the 2 800 millimeter shield walls. That's the foundation here, and then growing up, piercing through the existing building and reaching the level 19 and 20 to finalize the connection between the exoskeleton through the transfer plate. So if you look carefully on the right-hand side there, you'll see 2 more levels. The third one is not shown in this picture. The rebarring waiting to be completing work on the other side, and then pour from the top down the slabs of the new parking spaces created underneath the existing 2 ones. So in total, the building ended up with 6 levels of parking using the complete space underneath by removing the soil and gradually on small sequences progressing from one bay to another to complete the new foundation system. So in here, there are some of the photos taken during construction. On the left-hand side, you'll see there the digging continues right under the slab above, removing the soil and creating space for pouring the slab on grade first, and then going underneath again, removing the soil and opening space for creating the next lower parking level in there. So the caissons were in good condition, obviously, right? They needed, right, a lot of strengthening to integrate with the new system. What you're seeing here is one of the completed parking levels, the new ones, through the top-down construction approach. This was the operation that took quite a bit of time, but was well coordinated to get the soil out and then bring the materials in for the slabs of the parking structure and slabs and beams of the parking structure that were integrated with the existing caisson now in the exposed manner, creating the full parking structure, new parking structure. Now, I showed earlier the conceptual slide of the structural scheme that it was implemented. You notice in there that in addition to the gravity load, which for sure is critical, but one important component of the design was the lateral wind loading due to wind. So there were several challenges to address with regards to the wind design here. The first is related to the dynamics of the structure itself. Keep in mind that you are marrying a 45, 50 years old structure with a brand new one. And you don't have, right, the advantage that you have a fully controlled structure that you are designing from the day first, brand new. You are dealing with concrete that was poured 45, 50 years ago, and then integrating that into your model and put the effects of the slip joint in there that laterally integrates the two lateral systems with no action vertically, no interaction between the two. And then up above the mid-air foundation, you have a brand new structure. So where the frequencies, lateral frequencies of the building will end up, what kind of damping in the as-built condition we are going to achieve, and what kind of mode shape are we anticipating. So all these uncertainties needed to write a very detailed attention to make sure that the assessment of wind demand was as reliable as possible. And on top of that, that demand had to be optimized to meet the limited foundation capacity. If you remember, they were only the perimeter exoskeleton and that limited space on either side were within the property line to put the foundation that has enough capacity to absorb the loads. Other important aspects of the wind design were the motion comfort issues for the upper floors of the building, as well as drift. And one big question was how the design team could optimize the fatigue performance of the exoskeleton connections to the main building. If you remember, there is hundreds of those connections that are going to be in reverse loading during wind events. So all these led to a long-term program of evaluating the wind performance. We went through 9 iterations and through the different stages of design process of the building to reach at the point that the entire design team was confident and comfortable with the evaluation performance results that came through detailed analysis under wind action. So what you're seeing here is the ETABS model developed by the structural engineer. And what I'm raising here is a key question right on the left-hand side are what matters in the end is the as-built dynamic properties of the building, the damping, and the mold shapes. So those were monitored regularly as the structural scheme was tweaked and changed and modified to accommodate the loads that were predicted by the wind tunnel. So basically, we went through an iterative process through this to optimize and make sure that after each changes that was made in the structure, what was the impact on the lateral wave frequencies of the building and the mold shapes, and then plugging in those data into the analysis with the wind tunnel test data to update regularly and monitor what is the impact on the demand of the lateral loads. And is the lateral system able to accommodate those within the boundaries, the capacities, as well as the foundation behavior and stress levels. So we started I believe, in the initial wind tunnel testing in late 2012. And it was a period of almost a year and a half till we completed all the necessary iterations to give them green light into the wind loading demand, the serviceability performance of the building, and in addition to it, working with the supplemental damping system implementation. So these activities were going in every other step of iteration. So when we run the first set of results, and if you can see it here, it's what the findings were at that first round of analysis. So what you're seeing here on the green line are the wind tunnel predicted wind-induced accelerations. The first set of results is shown on the table below. And then also we evaluated the torsional velocity, the twist of the entire building. And that was a critical double check needed to be done, because keep in mind, you are adding a big transfer plate and then on top a huge mass. So actually everything twist about the transfer plate, and all that big twist is transferred down to the exoskeleton. So we definitely wanted to minimize and bring not only the accelerations, the sway motions of the building in both east-west and north-south direction, but also the twist, the torsional velocity. It's another index we check in tall buildings to make sure that during serviceability level winds, all these parameters are in line with the industry standards agreed as part of the performance evaluation under wind action. So what you're seeing here at the bottom of the table, you see that 1 year accelerations are at 15 milli-G, and then the 10-year 29. But much more concerning was the torsional velocities at 1 year were 7.2 millirad per second, way higher than what the CDVH tentative criteria back at that time was recommending. And the same concern and same level of exceedance was for the 10-year wind. So obviously something was needed to be done to address the serviceability concerns. So that was the first round. And I'm showing here just the 9th round of analysis. So we went in cycles in reviewing and rerunning again, and at the same time, all right, tweaking the structure to achieve the targets in terms of the stiffness we needed, both laterally and torsionally. So we reached a point where, with all the structural modifications of the integrated system, to get to a level where we had the torsional velocities under good control. If you see in here, at the completion of 9th round of iteration, we were satisfying the torsional velocity criteria, but we were still above the residential criteria at 15 to 18 milligi at 10 year, and then the ISO residential criteria here shown both on green symbol. So we had to close this gap now in performance, overshooting our accelerations to bring them down to acceptable levels. And in order to do that, because the structural modifications were fully implemented, and we reached the maximum possible level, we can address the improvement through this traditional, conventional mitigation measures. Then an implementation of the damping system was conceptualized in the form of the tune sloshing damper, the water damper. Again, with all this idea of developing the concept here right from the start, the consideration of the tune sloshing damper actually was a scheme that was very nicely integrated with the fire suppression system of the building. So what we achieve with that approach as an integration, the water in the tanks that will be used for motion control during winds, at the same time was integrated into the fire suppression system of the building. So in all, the implementation of the damping system actually could achieve 3 objectives from the serviceability point of view. First of all, it will lead to the level of motion acceptable for the tenants, being a residential building. Secondly, the same water will be used and for the fire suppression in case of need. And thirdly, with the increase of damping for up to total damping up to 2.8%, we reevaluated the lateral loads at service return periods up to 30 years, and we evaluated the reduction in the lateral load due to the contribution of the damper. And this improvement into the lateral loads, it will reduce the stresses into the critical connection of the exoskeleton with the existing building. So it's there are 3 benefits of coming from this system installed into the building. So the way this system was conceptualized, due to the demand to achieve the 2.8% total damping, there were 2 tanks, 10 meter by 11 meter in footprint, stacked on top of each other. And this is bidirectional, because if you look at the bottom portion of the component acceleration, for the 1 year, we had still needed to control both direction of motion in X and in Y. So the X component of acceleration and Y component of acceleration needed to be controlled or reduced at those levels that the total motions of the building are satisfying the industry criteria. Then due to the fact that they are stacked, and above it is the roof slab, the accessibility to the tanks was on the side of the tanks of access hatches. So one important consideration that in the implementation of the tune sloshing damper was monitoring the as-built frequencies of the building. So what you're seeing here are shown the levels where we, while building on construction, we monitored the trending of the frequencies of the building. So we started the first round of measurements when the building reached level 27, then continued up in other 3 more levels, collecting data on site and calibrating the S-measured frequencies with the predictions again from structural engineer. And in all those analytical refresh of the ETABS model, what was important that the analysis for prediction of the frequencies of the building at that corresponding to that stage of construction we were on site were done based on the as-built, as-poured properties of the reinforced concrete, not the one that were specified into the design drawings. The whole idea is to get to the closest possible prediction of the frequencies through the analytical model and compare those with the as-measured to see where we are going to end as we reach level 56. Because at the design stage of the damper, we had designed a damper to address the uncertainties with the variation to accommodate a variation of the as-built frequencies of the building for as high as plus 25% and as low as minus 10%. And this is a unique range that we use because of the uncertainties in how this integrated system, very unique, would behave in the real life. The bottom line is, since these systems put at the top of the building need to be tuned properly, optimally, to the as-built frequencies of the buildings, it was of particular importance for us to monitor and determine the trend. And based on the trend of the frequencies right at the level 52nd, we had to make a decision whether we need to adjust the footprint dimensions of the tune sloshing damper in order to land within the design tuning range. So it was a critical set of data that we had to collect and analyze in close collaboration with the structural engineer to make sure that we are making a critical decision at enough time in advance, so then the construction team can plan around for repositioning of the walls, checking the redistribution of the loads on that floor before the tanks were constructed. And here is a summary of all that process in this table. Those are the 3 yellow dots there showing this level 27 to 52nd. As you can see in here, the frequencies gradually drop, right? We were monitoring the sway in X direction, east-west, in Y direction, north-south, and torsion in there. So gradually, as the building grows, you see the frequencies dropping, the periods were elongating, was in the trend. And then with those 3 sets of measurements, we, based on the ratio of measure to predict it, what you see there, on the second set of data, analytical comparison, we then corrected, we anticipating that the building is going to be trending right steeper and the frequency is a bit higher. So we make the recommendation to the construction team to shorten the length of the tank by 1 meter so that we can land within the design tuning range we had initially. Because the design of the damper of TSD was done at the design stage, and the construction took quite a bit of time. So if you've seen here, we start in late 2012, and we are measuring in 2018. So was a lot of coordination and close communication to make sure that all the parties here, the mechanical engineer, the structural engineer, mechanical engineer, construction team were fully aware what needs to be done to properly implement the damper. Important thing is that we, with the set of the data we measured once the building pre-tuning, were very close to what we extrapolated through the measurements. And here is showing first before the numbers. I'm showing now the layout of the data monitoring system set up with 2 accelerometers, right, on north and south side, and then collecting data simultaneously to determine both the sway frequencies in X and Y and the twist, and using that as a baseline information to do the proper correction. But here is what the data were showing as we measured in November 16, 2018. So we measured frequency on the X direction as 0.217 hertz. And as we measured real one a year, almost right a year later at 0.219. So those frequencies shown in red dots there, those are the extrapolated from the measurements. So we were still down at level 52, and we tried to extrapolate those at the completion. So for the second mode, we extrapolated from the data at 0.240, and we measured 0.249. So we're very pleased with the process of extrapolating, and also most importantly, with the fact that we landed right within the design tuning range of the damper. An important piece of information from this table is that at the original design of the damper that was completed back in 2015, 3 years prior to measurements, those were the assumptions at the design stage of the frequencies. So as you can see here, right, there is a big shift into the frequencies, and that's why we were concerned and made the clear plan that we'll monitor very closely as the building grows the trend of the frequencies to make sure that we can tune optimally the damper. Now, once the dampers were tuned and then ready to go into full operation, we went on site. The tanks were filled with water at the recommended depth by RWDI. We went on in agreement with the ownership on a 3 years monitoring of the building as well as of the damping system in the as-built condition. So what you see in here, in addition to the accelerometers here, right, the small boxes in blue here, for each tank, there are 2 water rise probes here, sonar probes. One on each side, one on the north side, and one on each side for each tank and the lower. And we wanted to measure, to evaluate the performance, collected measurement vibration data simultaneously, and the building motions through the blue sensors there, and the gray sensors were monitoring simultaneously the water rise. But because this damper is bidirectional, its response addresses the motion in two modes: the north-south, the Y, up and down in the page, and the X mode, left and right on the page. So we had to measure simultaneously the water rise on 2 points or 90-degree rotation on the walls where they were mounted. And with this data, measuring simultaneously the response of the water in the tanks and the building, we were able to validate the level of damping we achieve in real life. And with those data, we went back to the wind tunnel analysis with the as measured building frequencies, as measured damping, and then reran the wind analysis to determine the service level loads and determine the delta, the reduction of the loads that also beneficially acts on the fatigue life of the sleep joint. So it's a multiple step approach coming now from the reality and back to the model that was represented as close as possible where the building landed at the day of closing the complete construction. So those data were critical to evaluate and to determine to evaluate the performance of the as-built condition. So for those that haven't seen any of the tune sloshing dampers and what's going inside those devices, I'm sharing this slide with you. And what you've seen here, there is on the top left is the access to the tank inside with where we mounted the water wave probes. So on the top right there, you see two little sensors there, one in the back, that is the north wall, and on the right, that is the east wall, the sonar probes that were measuring water motion when the tower was excited by wind. And on the bottom, you see the paddles. Those are the damping generating devices that are installed inside the tank. And those are, if you see there, those the blades of the paddles have some holes. So also that positioning of those is critical. And we determined that based on the November 2018 last measurements, so that the installers of the paddles would position those at the optimal width of the paddle. And in there too, you see a little a cable holding another device, and that is the water level sensor that determines if, for whatever reason, when they do the refilling of the tanks, they don't overshoot the height, and there is one sensor down in deep in the water with a certain delta that monitors if, for whatever reason, the water drops due to the leakage or failure in the waterproofing, to warn the central system, building maintenance system, that there is a water loss in the tanks. With regards to the data that we collected through this monitoring system, I'm sharing some data from March 2020 wind event in Toronto. And what you see in there, the upper plot is showing the responses of the building in acceleration, and well below the criteria. And this was a wind event with wind speed somewhere in the 65 to 70 kilometers an hour Toronto, just crossing the monthly wind events. So these motions are well below the levels that we were anticipating. And the second plot is showing the measurements in millimeters of the water waves, the wave heights inside the tank. So if you see in there are 4 readings. Top X, so the motion of the top tank in the of the water in the water rise in top tank in east-west direction, and north-south direction, top Y, and the bottom. And you see the water levels are slightly different because to achieve a robust performance of the damper, the water depths are set a bit slightly differently. So in that case, for any shift or predominance in one response of the other, then, and even for it's the building during with time loses a bit of stiffness, then we have a buffer in there to accommodate for those minor changes in the frequencies. So that's the idea that we came up with, the approach of tuning on this. And as I mentioned in the first slide, this is the first ever monitored full scale in real life a sloshing damper, bidirectional, bi-tuned TSD that is controlling the building motions, and in addition to it provides benefits into reducing the service loads and keeps healthy the critical connection between the exoskeleton and the main structure. And in the bottom, what you are seeing are the spectra of the measured accelerations in the building, as well as the spectra of the water wave. So basically what we have the alignment now as expected. We see multiple peaks on the spectra, which is due to the fact of the interaction of the two systems, right? This is now a coupled system, the building and the damping system, which responds in 2 modes, in the east-west and in the north-south direction. We went even further and checking now the solid line is the analytical prediction and the measures. The dots, the symbols are the measured responses, and the solid lines are the analytical prediction we had through our analytical models at the design stage of the damper. So that set of data gave us good confidence that even in such a very complex integrated system, with the damping system added on top of it, still we managed to deliver a performance in line with what was the design intent was for this damper. So with this slide, I complete my presentation, and I'll be more than happy to entertain any question from the audience.
Okay, great. Thank you, Dr. Bhuja. Interesting piece of construction, and then obviously a lot of monitoring that you guys have done, RWDI. I'm just curious. I mean, we'll take the questions. Just curious about RWDI provided more of a wind engineering, motion engineering sort of services. What was the interaction between the original structural designers and the foundation designers and RWDI, other than these 2 aspects of the design?
Well, the most critical thing was the big question, the way it started day 1, when I was brought in a meeting with the owner and the design team, structural engineer. Obviously, the key component here is they had a concept, right? A structural concept to work around. They had some ideas. But the big question that came day 1 for them is, how can we achieve and match what we have defined as maximum uplift capacity, right, on the foundation with all these very, very intricate operations, how we can get this confirmation that for the ultimate wind event and also serviceability demand, how can we get this right evaluated at the highest level possible from the reliability point of view. So in that meeting, it started day one. It just was concept from them. The owner had, the owner had the building right under his position for several years, but he was trying to do something with it, right? And the city allows right increased density, right, in Toronto. So he was ready for it, but he wanted right the professionals to provide some advice. So what in that meeting RWDI offered to them, we walked them through the entire process, a roadmap, what needs to happen to provide all the information and input and collaboration, what needs to be done. So they weren't aware, for example, that this is going to be definitely right a multiple iteration process. This is not going to be like a standard building that you have a full control of the foundation, lateral system. You have a perfectly right built and calibrated ETAPS model, whatever, and then you are ready to go. So you have full control. So there are uncertainties on the structural design part of things that are dependent on the input, on the demand. And then they weren't aware that this will go in a deep iteration. And also, in particular, the interaction between the structural engineer, say your team, and RWDI, very close. Reviewing the data jointly. I have been in their office on a regular basis. Not like the other standard one we do that you send a package of set of data and then voila, ready to go. No, in this one, because if you remember in the slide that I was showing the first run, the first cut of data, well, was a big issue. So we had to address not only sway motion, but certainly, and that came due to the fact that you have a lumped mass, a rigid mid-air foundation that drives that torsion. So you have to, because above the transfer plate, you don't have too much to do. Everything is right depending on the big, powerful spring, sway spring and torsional spring that is exoskeleton.
Yeah.
You are bringing in, and those discussions were part of RWDI with it, working on the dynamics, understanding the dynamics of these marriages. It's important because you might be off quite a bit in its built conditions, and then what? There is no turn back.
Fixing becomes tricky.
No, there's no more fixing at that point because you have
gone past that
with some very critical intervention down the building.
Yeah.
Keep in mind they went top down. So bottom up and then top down.
Yeah.
And everything could be on the structure. So three key things. We had to make sure that what supplemental damping we want was achieved because, right, you couldn't go further with modifying the structure. It's kind of structure is maxed out for several reasons.
Yeah.
You cannot go with bigger columns, right, sister columns, because you have 1.1 meter. That's the space. You can't cross the property line. So you have to work within those boundaries. Geometric bounds, material capacity bounds, and dynamics limitations, right? If we wanted to achieve with structure, then it wasn't possible. That little, we had a gap at the end, right? Between the demand in performance and then the target. And then the damper solution came right as a logical component into design, which nicely was integrated in 3 points of the performance of the building. So in short, Abhijit, it was a very, very interactive process from day one. Actually, on that meeting, I made the straight question to the owner. Do you really want to do this?
Yeah, exactly. That was my second question, but yeah.
Yeah. And he said, I do. That's what he said. But
Okay.
obviously, I don't know how to do it. So, and he said, I trust in you to walk me through this process. So there were two key things, was educational things,
Yeah.
components, and collaboration with the owner. The owner needed to know everything that was going to happen because some critical decisions were to be made. And he was also strong in the component that we are going to adhere to the sustainability design principles here. So picture that if you want to go in traditional approach, you have to demolish
Bring it
the
down.
entire
Bring
building.
it down and cast new.
And then you are in downtown Toronto. You are going to move material in and out, right? And then you start from the scratch and build a new one.
Yeah.
So it's on top of that, the reusing the existing structure was the key point of discussion. To what level we'll keep as is. Concrete columns of the building as is. But the foundation needed, right? If you saw the caissons poured in 60s, right?
Yeah.
It's not the technology we have today, right? We have good control and quality. And those ones had to be retrofitted to come up, add more capacity and stability laterally with the slabs. So
yeah,
it's the key word here is day one. Go and then till the end. It's been 2012, 2019, so 7 years in the making. And all of the design team, NRWDI, was regularly in contact, communicating, meetings to make sure anything that they were changing, we needed to know. And between the first iteration and the 9, if you notice, it's almost a year time. Yeah, going through that. Yeah.
And I mean, there's so many questions, but I'll probably read through the questions and we can pick some of the critical ones because there are some questions which are related to more on the structural design and the foundations. I'll run through that. If you have some lights on that, lights to throw on that, you could.
Yeah.
But before that, just one question in my mind is design liabilities. You know, the existing building, which was done back in 50 years back, and now you're putting in a new building with some interaction with existing building and its own foundations or columns. Who carries the design liability in this situation? Is it the new designer who took that, a new structural designer, or is what sort of a joint responsibility between the two?
No, at the time because the new designer did the structural assessment, right? It went on site, non-destructive measuring the concrete and all that. And he takes over at that point, the structure. The old designer, all right, is out of responsibility. The new designer takes
full responsibility.
Yeah. If you do a structural assessment, and I've been through those discussions, I've been part when those are discussed. If you go and do a structural assessment, right, and then write a report that's what I found, and then you make a recommendation that these data provide enough information to inform the design decisions for the next stage. At that point, the old designer it's not anymore into the
Okay, so let's go to the questions now. Pulkit has written, I'm going on question answers and then we'll go in chat box because there are some questions in chat box as well. I'll first go to Q&A and then we'll go to chat box. Pulkit written, can you please throw some light on philosophy adopted in detailing of transfer beams 3 meter deep and 800 millimeter structural wall joint?
Okay. let me throw some of my knowledge that I have through all this interaction in the process. So the 3-meter deep beams are sitting on the wings of the shear walls at the top. And then they are taking, because they are taking the full length of the building in the long direction, right? And they are also supporting of the other secondary beams, shallow beams that go up to the perimeter beam or tie belt all around.
Yep.
So the idea was to take those big beams controlling the 55% gravity loads of the new building. In order to do that, they were stretched fully east, north, south, and then with cantilevered portions to take the tributary gravity loads and transfer that down through the shear walls. Now, picture that. The shear walls piercing through the existing building.
Yes.
They don't share any gravity load with the existing shear walls that are right by each other. There is a slip joint as well between the shear wall and the new shear wall and the existing in those mechanical. They are close enough that through the slab action, they engage laterally with the core, but not vertically. Then the slab go up, stretch out, on the beams at the top first. And they take the gravity, the tributary gravity loads to each of the tubes of the exoskeleton, each of the columns. And that gravity load goes straight down through the sleeve joint on each column of the wrapping around the existing column. Then there is no gravity load, that is shared with the existing. Laterally, at each floor, you have 2 mechanisms transferring the lateral loads from the wind to the exoskeleton, and then to the central core and the beams. The slab is connected to the external exoskeleton itself with a connection, and also the 2 columns are connected at one point at the top. So basically, you have a completely gravity load system that comes up and redistributed to exoskeleton and foundation. And then laterally, you have an interaction between the shear walls and the existing core and the concrete columns and the exoskeleton columns. So very clear system, gravity coming independently, laterally they talk to each other. They don't talk gravity-wise.
Gravity each other. Okay.
Yeah.
Okay. Second question is, I'm not sure whether Toronto comes under seismic or high seismic, but there's a question. Please also explain seismic criteria considered for the transfer elements of the design.
Well, the transfer elements, once you have, because seismic, is just a different type of load that comes, laterally, First of all, Toronto is not any highly seismic, so that was part of the early design.
Advantage, yeah,
and the check mark, in the evaluation.
Yeah.
I don't think they would be able to do it in Vancouver, West Coast, or somewhere else, Seattle, all right. So that was part of consideration, firstly. Secondly, when the model was calibrated and validated, then the distribution, and that's what structural engineer couldn't wait till the end. We measured the frequencies to see how close this model predicting, the periods of the building, and also the mode shapes and what damping we are getting. So that is another contribution, but not necessarily any specific due to the low seismic. Everything was driven by wind. Seismic forces weren't coming into the picture. But the distribution of the loads to answer his question, the distribution of the load, certainly the transfer level attracted quite a bit of inertial load. Yeah, that's.
Samir is asking a question about how much damping found on measurement and which technique were used, random decrement, etc.
Yeah, the technique was random decrement, and the evaluation, right, for the as-built condition was a methodology we have developed with simultaneous measurements of the responses of the building, responses of the damper, and the as-measured damping of the system. So 2 stages, right?
Yes.
The damping that we measured was slightly lower than what we assumed, from 1.5, because the building actually behaved pretty much almost in this, due to the stiffness distribution, almost right linear, and with a bit of shear deformation driven. So we got some damping right close to the typical we assume for reinforced concrete building at 1.5%.
1.5%. Yeah.
Yeah.
Samir has another question, that what was the difference between the structural frequencies computed using the analysis software ETABS and measure? I think you've shown that.
Yes.
There's a comparison that you've shown. But I
Yes.
have a follow-up question on that. Is
Yeah.
when you do accelerometer measurements, and you got to have some force to excite the building of some sense. So
Right.
was the excitement of the building done by natural wind coming in there, and that was the exciting force considered?
That's a very good question. Actually, was wind excitation. But
Wind excitement.
again, we are lucky on this, and that was right because this project is the backyard of RWDI. You jump in the car, and in 40 minutes you are on site. So we were monitoring the wind, and then showing up and getting measurements. Wind was it. We related everything to the wind excitation.
Okay.
Ambient excitation, right, especially as the building was growing, it was attracting more load, right? So the level of responses were higher. So we had the right level of wind excitation at the magnitude that the data of responses of the building were right very clean and not contaminating our readings. Well, the key point is to watch the ratio between the noise, ambient noise, and responses. Yeah. So the difference, well, let's go to the difference. That's an important one because it's important for all structural engineers that are attending this. As we know, there is guidance in the concrete standards, right? About when you expect level of cracking as the building crosses day 1, right? And there's some recommendation there and suggestions what kind of correction into gross moment of inertia of members of the lateral system you should consider. Well, those are suggestions, and each of the an assessment, a proper assessment of what kind of stiffness you are losing at 1 year, at 10 year. It's an important step into providing that information to us. So if you notice there, the initial assumptions are standard because Canadian code offers also, similar to ACI, American Concrete Institute, some guidance. And the structural engineer imposed those. Then that's where our WDI comes in as a wind and structural dynamics consultant. Say, hold on, those are assumptions, but we need to monitor with you on a regular basis what the code is requiring you to do, which is fine, but also a bare, fully non-corrected model, brand new, fully no cracking modifiers. And we need to see those as we do this other iteration.
That process.
So we were requesting to them in parallel all that. at the very end, to answer the question that came in, we work with structural engineer to get a representation of the S supplied and data from the concrete strength and as measured from the samples that were put in the building. So it was a rebuild of the structural model with the as-built condition. So at that point, once you are entering the stage of the as-built, the model is a reference. The reality is the focus. You are now not completely disconnecting from the model, but you focus on reality and try to understand how the building is behaving now. And does the adjustment of the model based on the as-built conditions, being the joints or being any changes that was done. Mind you, the full design completed 2015, including damper. But the building, when we went measurement, was 3 years later.
Yeah.
So all these interfaces between the slip joint and the exoskeleton, the connection of the transfer to the main supporting structure, the friction between the big shear walls to the existing in the slip, there's a slip joint right there. And those are other things that kick into the reality. Obviously, you can capture that into the ETAPS model.
In the ETAPS model, yeah, exactly.
The slip connection of the big shear wall with the core that was built on 60 and with the material in between to allow the gravity transfer. But the difference we identified right away was based on initial assumptions with some potential cracking. One important thing I want to mention in this conversation is, and it's something that structural engineers, well, by the way, I'm structural engineer myself. I started designing first. Then I went to the other stuff, the dynamics. But it's important to pay attention into the all these cracking assumptions that you are making. It's not just because you think that the softer building, if I drop the frequency or increase the percentage of correction in the lateral members, will giving me more conservative loads. There are situations, depending on the wind spectral response, that not necessarily so. So don't disconnect from your baseline model. Keep that in there. The one that is fully elastic in the best representation of day one. No wind, no earthquake. And then things will happen. Secondly, when we introduced in the building a damping system, then you are getting an advantage, because this device is keeping a good health of your structure in terms of stiffness control. Why I'm saying that? 2 kilometers away from this project, we completed 6 years ago another project there that we monitor also for 2 years. And after 3 years of monitoring, we confirmed that the building is matching exactly what the structural engineer predicted in the elastic model. But the damper generated 3.5% damping. So we went 4 years later after the commissioning, we drained the tanks. We measured again damping, the inherent damping, and we measured the frequencies. Even if some 10-year wind event hit Toronto at that time, no shift in the periods of the building. The same what we measured prior to commissioning the damper, the same 4.5 years later after we drained the tank, because you need to drain the tank, right?
Yeah.
Avoid the interaction.
Yeah.
So what I'm saying, that health of the structure is being protected by the damper, because if it starts to initiate the dynamic load cracking will
cracking
start
more.
if you
Yeah,
don't
start
have the
cracking.
dam. So
Yeah,
that's something to keep in mind. It's not just servicing you to keep the tenants in good shape. Actually, from the structural engineer perspective, it's keeping a good health of your
health
structure.
of the building. Yeah.
Yeah, yeah.
Okay, so there's a question on foundation. For construction
Yeah.
of additional parking below ground, soil support around the chasm was removed. How the reduction in the load carrying capacity of chasms due to loss of soil support and a side friction was considered or compensated in the design?
Yeah. Again, this answer of this question, I'll go back to the initial assessment, right? As to what remaining capacity had the caissons, right? One good news after that, that's what I said, there were three key factors that allowed this to proceed. One of them was this, because the caisson capacities, right, were way for an 18-story building, were having plenty of capacity in there. That gave them the confidence to, yeah. And temporary, in the pictures there where the cleaning up, right, they are one side, and temporary they had right horizontal bracing to make sure that there is no oversight.
Effective lengths and all things.
Yeah, all that, yeah. But the process, once they cleaned that, the bracing came in right away, right, with the slabs and the beams.
Yeah. This was from Suhas, and then there is another question from Samir. Does damper design length and depth ratio of the TST was done after the measurement of actual frequencies or before? I think you mentioned that you designed it and then you revalidated it.
Yeah, it's part of our procedure to stay right very close. So basically, the 52 level 52 measurements, when we did the extrapolation exercise, so extrapolation is a kind of a blind prediction with three sets of data. But we have come to the understanding that that gives us a very good feel what the end frequencies will be. So the recommendation, the short answer was done right at the end of the third round of measurements, and then coordination with the construction team and structural engineer to check the load transfer. You are shifting the walls, right? Yeah. So that's happens right after the typically 90% completion of the structure. We do that.
Yeah. I think you answered this Samir's question. Joe has said that very elegant presentation. Thank you, Joe. Joe Kalako. I think Joe had some comments also in chat box.
In the
come
chat?
to that later. Yeah,
Okay.
I'll come to that later. Let's finish up the question answers. Samir had further question about if the nonlinear simulation of liquid sloshing done numerically, then it were verified experimentally on the scale down test or later after installation of TST. I think you mentioned that you did it on the actual model, actual building, isn't it?
Yes, but I think the question has merit there, because we need to understand how we develop those models. The models were developed based on the model scale shake table testing. So back 10 years ago, we invested in evaluating performance of bidirectional TSDs on shake tables, including so we have calibrated everything through that model that is in the shake table data. But now this is the first time we are validating in real life. So what you saw there, the sonar, is exactly what we're measuring on shake table test model back, but this is a real thing. So the base of design is developed based on shake table testing and full analytical modeling. The other one is now we are saying, does our model, we design these things, how does it match the real life? That's what, and to our knowledge, this is the first ever done in a bidirectional TSD.
Yeah. Omar has a question on chasms. Was there any test done to the existing 50 years old structure, especially the caissons, whether they are still an acceptable limit of strength. I think you did answer that, I believe.
Yes.
Yeah.
Yes.
So it was. Samir has a question. Drift of the building corresponding to a higher return period when, like 20 or 25 years, was TST designed for corresponding wind speeds?
Well, there are two things there. The design of the TSD to take the ultimate loads and then share those with the structural engineer, so then those loads are absorbed. Then there are, let me go into two steps answering this.
Yeah.
The way we do design the dampers, RWDI Motioneering, the group that does the damper design, it's fully based on the performance-based design principles. And we have been doing this since 2005, almost 18 years ago.
Yeah.
So what it is, we go into performance analysis with all this analytical model we have developed based on the validation through the SEG table. We start with monthly wind events, monthly, 1 year, 10 years, 30 years, 50 years. And then these are serviceability range of wind loading. And then we go into 500 and then onto 1700 if it's US, right?
Yeah.
Canada are 500, and then this goes for each wind direction, and everything is done in time domain. And there is a model, structural TSD interaction with all the fluid motions here. And this is run for 36 wind direction and scaling the wind properly. Then comes seismic from service, 50-year service level seismic wind event, design level, and maximum credible.
Maximum.
And these are for determining, right, the forces that are seen onto the paddles, and also the four interface forces, pressure distribution of the tank walls. And we provide a detailed set of wind loading scenarios to the structural engineer to design those properly. So there are loads on the walls, overall loads that transfer from bottom of the tank to the main structure.
Okay. Suhas has a question. Any special measures were taken to ensure stability with respect to wind-induced oscillation during construction, as the sloshing damper could be only installed when the building was completed? So basically, he's trying to figure out what was the consideration during the construction of the building.
Yes, that one was done analytically to see what level of motions we are anticipating with our damper. So there is one thing important here. The aerodynamics of the building during construction and as completed changing, right?
Changes, yes.
So that becomes, right, a bit very convoluted exercise. But with the assumption that everything, right, it's aerodynamically performing same way, which is not the case, then we're checking levels of accelerations. And those ones are, keep in mind, that there are limitations for rules for safety in Canada. Once winds hit 50 kilometers an hour gust, then construction activities are stopped. There is no. So basically, in terms of impacting if the motion of the building were there impacting the people that were working or not properly doing the job or creating any concern, it's not an issue, because at those level of winds, beyond that, it's more of what we typically do. It's nothing directly related to that, but it's weather forecasting provided to the general contractors.
Okay.
To warn them that, right, this gustiness, wind gusts are coming. So you do proper 24 hours in advance warning to properly secure everything in the building that is not taken care of properly, and the risk of flying away. But in terms of the level of displacement that the building sees at below those winds, mind you, our predictions are at the 50.
Yes, 50
level,
level,
right?
yeah, yeah,
So everything attenuates quite a bit.
yeah. And that too, your facade may not be fully loaded on the building, so the
Yes,
wind might
yes.
just pass through as well.
Yes, yes.
Samir has another question. Since the frequency of the building were decreasing from what it was originally designed, how much reduction in the acceleration was achieved in the revised wind tunnel testing?
Yeah, so that was part of at the completion, right? That's what you saw the responses that we predicted. The margin we are trying to narrow, right, was not right. Still needed to be taken care, right, with those properties. So basically, we had more to do, more on the 10-year wind, right, with the as-built frequencies rather than the 1 year. One thing, though, we have to keep in mind, as the building frequencies, as built conditions, end up higher, then ISO criteria is frequency dependent. So actually, the criteria becomes more, more stringent. So it's a kind of, you have to watch it, all right? It's not a net benefit that the increased stiffness comes in. Reduced acceleration, but at the same time, the criteria is kind of going more stringent, so it's dropping. Right? So you need to meet a more stringent target.
Yeah.
So that's why all these things are part of the consideration and informing the design team and the owner that this is what is happening and this is why we are doing this. So keeping everybody informed that the loop and in the process.
Yeah. Ashok has a question. How about the soil structure? I think he meant to say soil structure interaction with the existing caisson was dealt with while removing the earth all around the caisson to make way for forward basement. I think you did answer that during the construction. You said they were braced and then they were braced eventually by beams and slabs.
Yeah. So what I showed in there is the last part in the core area. Out of the core area was easier because you can go right in a single caisson, right? But you had a large operation there when you put the shear walls.
Yes.
So basically on that portion, this is not that everything is left right unrestrained. They were on a caisson by caisson base, right? And if you see the slabs coming, they came from the side, which was easier, to the center. So most of the caissons were braced already with the slabs. And then they were letting the last one and to close the bracing of the wall. And as they're progressing, they did for the single ones, they did the retrofitting first, and they kept removing. But was on a caisson by caisson basis. But the key starting point is that the capacity, the extra capacity was huge. That gave them confidence that they can do that thing.
So sometimes you have advantage of old structures. I think you're not designing to the minutest of the flip, safety margin.
I doubt you go into that with designing the foundation. Maybe you know better the structure, but with the foundation, it's a risky exercise. You need to have that level of comfort that there is plenty of safety margin there to play with.
Vikash is asking question about who is the structural consultant and architect of the project.
The structural consultant is Ziggy Sudak. It's a Toronto firm, a mid-sized firm that has done quite a bit of high-rises. And one of them, you might have seen, it's in Mississauga, some twisting towers.
Okay.
Yeah.
That's the one.
And the architect is Core CORE Architects,
Oh.
both Toronto-based.
Okay. Okay, let's go to quickly on the chat box.
Okay.
I'm just coming from top. Where is the chat box? It is. Interesting example. Kalyan Ganguly writing eye-opening ideas. Fantastic. Joe has a question. It would be good to mention the structural engineer was Sondak. I think we
Sudak.
discussed about Sudak.
Yeah. Sudak.
Yeah. Then Joe has some questions here. One is, how did they build the caisson for the new sister column of the exoskeleton column right next to the existing column?
Yes. So basically, right, you are digging around on the east side of, I'm talking about east side first. You remove the soil on the east side, right by the footing of the columns, and then you go right with basically you are going right from top down, and then as you come at the bottom, right, you complete the foundation. So it's tacked into the caisson and then stretches out up to the top surface. So at the bottom, the two are connected because, right, once you have the other column at the bottom, there is not much, right? You have a system, right, with slab and the two columns, right, linked together. So basically, they are taking, from that point on, they are taking, right, the tributary gravity of that load, all right, on the sister concrete piece of that addition to the column next to the existing one. So you get the two columns side by side, right, with a small gap between them, and the same gravity it's coming right on the vertical exoskeleton column, and laterally they are braced by the slab that runs from east to west. So laterally they still, right, are connected. Vertically, right, they are right on separate, right, accommodating the shortening themselves. But at the end of the completion of the superstructure at the top, they measured, right, how much of the shortening, right, was accommodated to the slip joint. So it was something like on the 32 millimeters, so 3 centimeters. And then
Did they lock it afterwards, or they just left it?
no,
left
it for future, because you have to have also consider the additional shortening
the
when
movement.
from wind. Yeah.
Okay. BSC Rao says extraordinary cutting edge engineering, thrilling concept. Joe has another question. Presume the office was vacated during the expansion. I think you did mention that there were some floors which they were vacated where you are placing the facade, but other floors were still operational.
Yes. So the entire office floors were fully occupied, and the elevators, right, that were servicing those were still, right, working like before. The three operations starting building the exoskeleton, but the completion of, as we're going higher 2-3 floors, removing the old facade, they were completing, the other team was completing, right, the insulation. Because the construction took quite a bit of time, right? And it went
so to run in parallel.
Yeah, they went in parallel, and then they went through, I think, two or three winters totally. Yeah.
Canadian winter.
Yeah.
Okay. Joe's question is, hard to believe that this scheme was more economical compared to demolition of existing building. I think you did mention that in downtown, midtown Toronto, I think you had different challenges of material movement and other stuff.
Yes. It's a quite a bit on the numbers. I believe, right, in the end, you have to keep in mind that it has to make sense business-wise, right? Otherwise,
Yes.
so definitely, right, those numbers were run very carefully to make sure that goes in that way. Yeah.
There's a question from Ashok. How about side interaction of existing Kasam dealt with while removing? Okay, I think it was repeated in the
Yeah.
question answers. Then thank you for basically thank you. That was the wonderful presentation about the marvelous piece of engineering. Sangeeta says wonderful presentation, excellent engineering feat, says Umar. Bala Murugan, it's a pretty long name. Excellent webinar, very good. Rajanikanth says excellent sharing, valuable novel experience. And Alok is writing. I think Alok signed off, so that's probably the reason he was writing a long essay. Wonderful information. I have to leave now. Who was the second? We discussed that.
Yeah.
And I think yes, that's more or less there. Great stuff. Very well done. Very well, articulated. There's a lot of engineering behind all this, but you put them in a picture. That was the best thing. The people can see the picture and feel it rather than just putting text. So that was a great.
Yeah.
And then really, really wonderful piece of engineering. Thank you
Thank
very
you.
much.
Thank you very much. It's been really a very, very interesting, challenging project, but a lot to learn through this. Certainly, right. The structural engineer had all that gut and push and adrenaline to really take on
Yes.
something. But again, the key message I'd like to share here is that the close interaction between the structural engineer and the RWDI and machineering, because they were directly related to the structure. Obviously, the other disciplines were doing similar things, right?
Yeah,
But
yeah.
in terms of moving forward with the project, they needed that comfort level that we need to know the upper bound of the wind demand and how can make things happen. That was in short the story. But yeah.
Excellent.
And
Thank you very much for your time.
yeah, you are
and then,
welcome. And if any other question, Abhijit, comes from any members that
Sure.
it intrigues them or they want more detail, I'll
Yes.
do my best to answer those whenever they come.
Great. So with that, gentlemen, ladies and gentlemen, we'll close today's session. Hope to see you again sometime in the future. Good evening, good night, good day, wherever you are in the world. See you then. Bye.